And also let me tell you what M is in this case. So here, M is going to be three-dimensional. So this is going to be a compact, orientable, three-manifold. It can have boundaries. Let me say that the boundary of M is either empty or toroidal. So that just means that it's some disjoint union of two tori. And the last thing I want to say is that M is irreducible. And has positive simplicial volume. Okay, so let me tell you what some of these mean. I'll assume you know what a three-manifold is and what it means to be compact and orientable.
Yeah.
But I'll tell you what irreducible means. It just means that if you have any embedded two-sphere in your three-manifold, then it bounces a ball. Okay. So in particular, an irreducible three-manifold is not a connect sum, for example. Okay, I'll tell you a little bit about what it means to have positive simplicial volume without actually defining simplicial volume. But something that is true about positive simplicial volume is, for example, that the fundamental group is going to be infinite. So if you have an infinite fundamental group and it's irreducible, this is equivalent to saying that it's aspherical. So that means that all the pi k's for k's greater than 1 are trivial, for example. Okay. So let me tell you a little bit about simplicial volume. So simplicial volume so this is a homotopy invariant that was defined by Gromov in the early 80s. So this is classical. Or my definition of classical is anything that was from before I was born. So I think this is classical. It's also called Gromov norms because it was defined by Gromov. What it is, it's really the infimum of the sum of the absolute values of coefficients over all the singular chains that represent the real fundamental cycle of M. Okay. However, there's another way to think about it in terms of geometrization. That's all I'll say about this. So this was introduced by Gromov. Maybe early 80s. Let me tell you first about geometrization. So the geometrization theorem, which I guess the first part was, or part of it was due to Thurston in some cases, and this was also in the 80s, I think early 80s, but it was resolved by Perelman famously. And what geometrization says is that if you have such a three-manifold, so for such M, so here again, I'm assuming it's compact, orientable, irreducible. Oh, I'm not assuming this part. Sorry. Let me just say it.
You're assuming it's closed.
Yes, but you can still say it for compact when the boundary looks like this. So actually, let me not say such M, but let's say M. Oh, you're right. Let me just say it for the closed case. So if M is closed, let's just state it for the closed case. So M compact with empty or toroidal boundary. And irreducible and orientable. Put this off. So if M is compact with empty toroidal boundary, irreducible and orientable, then it can be canonically cut along embedded tori So this is two-dimensional tori, such that the resulting pieces admit a finite volume geometric structure. Okay, and color. So this finite volume geometric structure is uniquely modeled on one of 8 choices. So there's going to be 8 different model geometries. The first one is E3, so that's just R3 with the Euclidean metric. There's S3. Like this, okay. H2 cross R, S2 cross R, mu, so, and the universal cover of PSH1. Is that 8? Yeah, that's 8. Okay. So that's all of them. Okay, and this composition, like I said, is canonical. There's a particular way to call it. This is also called, well, a different color. This is called the JSJ decomposition. J stands for Jacob, Shalin, and Johnson, and it's not alphabetical because Jacob and Shalin did it independently from this one. That's why it's written like this. But I think JSJ also sounds good, right? Anyways, so this is the JSJ decomposition. Actually, the JSJ decomposition was introduced much earlier than the geometrization theorem, but it turns out to be what you need to cut it into the right pieces. So now I can tell you sort of an equivalent statement to saying that you have positive simplicial volume. So M has positive simplicial volume if there is at least one hyperbolic piece. At least one, let's say H3. Okay, so here's a picture of what M could look like. This is how I draw a free manifold. And there's a canonical way to cut along some tori. Let's say here's some tori. And at least one of these pieces, let's say like this one in the middle. So this piece, I'm going to call it NH. H for hyperbolic. This is going to admit a hyperbolic structure. So what that means is that it's homeomorphic. So this is homeo to a quotient of H3 by some group that acts by isometries properly and discontinuously. And this has finite volume. And here, when I talk about volume, this is the volume that's induced from the hyperbolic metric. So that can be true. And in this case, when you have these boundary components, what it really looks like with this hyperbolic metric is that you get, these are called cost neighborhoods, and they look like a torus cross array, but it gets smaller and smaller. And this thing, you can find this thing with finite volume and a hyperbolic metric. Okay. So this is sort of what M looks like. There's at least one hyperbolic piece. Okay. And I'll say that if you combine some work of Gromov and Thurston, actually you can see that simplicial volume is proportional to the sum of the volumes of the hyperbolic pieces. So non-hyperbolic pieces don't contribute anything to simplicial volume. Okay.
So it's only one type out of those
8.
8 types. Which,
Yes.
Which is
Yeah,
confusing, I see.
that's right. Yeah, so there are many reasons why this geometric structure is the most interesting, but this is one of them.
Yeah.
Okay. Okay. So also maybe I don't have to write so big because this room is not that big. But I'm kind of used to writing big. Okay. So let me tell you a little bit about what we know about such manifolds. So what we know about them. So the first thing is that I already mentioned this, but the fundamental group is infinite. But there's actually a lot more that we, and actually not, and also non-solvable. But also there's a lot of really big theorems that have come out about three manifolds, I guess, in the past 10 years or so, so not yet classical. So the virtually special theorems, I'm gonna say it like this, but there's really a lot of work that goes into this, and I'll mention some names. So I guess the main result here is to Abel. This is a $3 million result. He won the breakthrough prize. That's $3 million for this work. There's stuff of Abel, there's stuff of Weiss. Most of their stuff was particularly in hyperbolic three manifolds, but when I want to look at more general three manifolds that have a non-trivial JSJ decomposition, I need some extra work. So let me say here, I'm just going to write it down and I'll pronounce it. Okay. That's a lot more work. But some consequences of these virtually special theorems that apply for these manifolds that I'm talking about today. One thing is that their fundamental group is virtually large. I'll tell you what this means. Let's do a color. So virtually means that, well, it might not be, but it has a finite index subgroup that is. And large means that you have a surjection to a non-abelian free group. Okay. Why is it nice to be large or virtually large? Well, free groups have a lot of subgroups. So if you surject a free group, you also have a lot of subgroups, which means that you have a lot of finite covers, for example. So that's quite interesting. Something else that's true about being large is that the first Betty number is then at least 1. Okay. So again, first Betty number is the rank of the C part of the homology. Okay. And also the virtual Betty number, first Betty number, in this case is infinite. Okay, what does this mean? It means that if I pick any large number, let's say n and C large, then there exists a finite cover such that the Betty number, the first Betty number of this cover is at least this large number. Okay, so basically, it virtually has a Betty number as large as you want. So we say it has infinite virtual first Betty number. Okay. Okay, so in particular, that means we can like construct towers of covers where the Betty number grows as much as you want. And maybe the last, there's a lot of other consequences of these theorems, but let me just say one last one that will be useful. And this last one that will be useful is that I1 of M virtually retracts to its relatively quasi-convex subgroups. Okay, so let me also tell you what I mean by this. So I'm going to say that these types of subgroups is not all subgroups, but the nice subgroups. And by virtually retracts, I mean that there's a finite cover. Again, finite cover. Oh, and let's say I have a relatively quasi-convex subgroup called H. Then I can find a finite cover and a map, let's say R. From the fundamental group of this cover to H, such that it restricts to the identity map on H. Okay, so that's why I call it a retraction. Okay, and this will be useful. This will be useful later. Okay. Okay, great. So one thing that we saw is that it has virtual first Betty number is infinite. So again, like I said, you can find towers of covers where the first Betty number grows, and it can grow as large as you want. But how fast can it grow? So that's obviously a natural question to ask. And the answer is not so fast. Okay, so here's a theorem. The theorem of Luke, also combining work of Lot and Luke. And what this says is, again, for these type of three manifolds, if you are given a cofinal tower of regular covers, okay, so it looks like this, and we call them 0. Regular finite covers. And 1, and 2, and so forth. So I have this tower of regular finite covers. Regular here, I mean that normal. I guess sometimes people say regular, sometimes they say normal. They say normal. And cofinal means that if I look at, say, the fundamental group, so these all come from finite subgroups, if I look at their intersection, it's trivial on all of them. So that's what cofinal means. Okay, so if I have this, then if I look at the limit as I goes to infinity of the first Betty number of mi, and again, remember, this is homology with integral coefficients, and I divide it by the degree of the cover. Okay, this is 0. Okay, so again, I just told you that you can find these towers of covers where the first Betty number can get as large as you want, but the rate at which this happens is very slow, at least compared to the degree of covers. Okay, so that's what this tells you. Okay. Okay, great. So we sort of understand sort of what's going on, at least in terms of the first Betty number. But what about torsion? So there could be torsion in H1. So this is what I want to talk about next. So we don't have such a theorem in the case of torsion, but we have a conjecture. So let's take a conjecture. So here's a conjecture. And this conjecture is, I guess, a special case of some bigger conjectures due to several people. Let's include Bergeron and Venkatesh. There's like a version due to Luke. There's a three-manifold version due to Le. So I'll just say all that. But for this case, then this conjecture says that there exists a cofinal tower of regular finite covers such that, so again, if I look at the limit as I goes to infinity But instead of the first Betty number, here I'm going to look at log of the size of the torsion in H1. Like this. Thanks. And over the degree of the covers. Okay, so this conjecture says that this should actually go to, I'm going to put quotations here, to the superficial volume. Okay, so the conjecture is a little bit explicit. It's like some specific constant times the superficial volume, but I'll just say this. Okay, it's just a conjecture, so we don't know if it's true yet. We can prove, I guess, an upper bound for it. So this is an upper bound of this limit, but we don't know that this is fully true. But anyways, so we have this, and it has something to do with superficial volume. Okay. So it's a conjecture, so we still don't know very much about it. But even before we try to get to this conjecture, we should learn a little bit more about what happens if we can make it grow at least. So in the case of the first Betty number, well, we know how it grows or how fast it can grow, but we also know that it grows. Okay, so in particular, maybe we should ask is, can we at least check that the torsion can grow in finite covers? So this is a question that I'm going to try to understand. And in this direction, I guess the first result in this direction is due to Soon. This is something Soon in 2015. Okay, so fairly recent. And he showed that if M is a closed hyperbolic free manifold, okay, so this is just restricted to the case of closed hyperbolic 3 manifolds. Then M virtually let's say has any virtually has any prescribed torsion. Homology. Okay, so this is what Soon said, and so we were able to generalize this. So I'm going to say a theorem. And here I'm going to let M be as general as I said earlier. So this is compact, orientable, irreducible, M to toroidal boundary. And positive superficial volume. Then, again, M virtually has any prescribed torsion. Okay. Let me also quickly tell you what I mean by prescribed. So here is that for any finite abelian group, okay, I can find a cover. So I can find a cover where A is a direct summand in H1 of the cover. Okay, so that's what I mean by virtually having any prescribed torsion. Okay. Also, let me tell you a little bit also about why this is necessary. So if you remove positive simplicial volume, then it's not true. Okay. It's not so hard to see that if you understand a little bit about cipher fiber spaces, but I won't talk about that today. But yeah, anyways, if you remove this, it's not true. So you sort of need this, but you'll also see how this is very much used in the proof. Any questions?
So it's quite a big generalization of the previous theorem, Soon's theorem, because there he basically assumes that it's one component in Thurston generalization.
Yes, that's right.
You're saying that it's just enough to have only one component, like in his theorem.
Yeah, that's right. But I will mention that there is something that, well, I'll mention it when I go into the proof a little bit. But there is something that we use very heavily here that didn't exist in 2015. So there's some machine. So in 2015, what did exist was the work of Hanna Markovich, which also won them the Aaron Prize. I think that's how it. I don't know what it's called. Something with A.
Aaron Prize.
Yeah.
Aaron Prize.
Yeah. So that came out around like 2010, 2012, and that machinery only works for closed hyperbolic three manifolds. But then more recently, around 2018, is when a preprint came out of Hannah Wright, where they generalized it to hyperbolic three manifolds that are not closed. So that didn't exist back then, and it existed, and we definitely used it here. So someone couldn't have done it earlier. It's also a point. But
what's the
yeah.
name of your co-author?
Daniel Gross. Sorry, I wrote that when I wrote the title.
Sorry.
But I can write this. This is Gross. Okay. Other questions? Okay, so let me just talk about some ideas of the proof. And here's the main idea is that, say I'm given M and I'm given A, okay? So A here is this any kind of abelian group that you choose. What we'll do is, we'll first look at the hyperbolic piece, and we'll just call it MH. So this is going to be a hyperbolic three manifold that might have some costs, okay? So it might have sort of this boundary that looks like it's torus plus array. And the goal is to construct a two-complex X that immerses into MH, okay? But I want this immersion to be really nice. I want this immersion to be almost geodesic. I want it to be pi1 injective. And I want it to be far from these cusps. So these are the boundaries. And I want it to be such that, well, now I have that the fundamental or the pi1 of this two complex embeds into the pi1 of MH, but I want it to embed as a nice subgroup. So I want it to embed as a relatively quasi-convex subgroup. Okay? Because if I have all of this, then I can use these properties that we get from the virtually special theorems to get a retraction from, or get a virtual retraction into this group. And we'll see how this is useful. Oh, I forgot to say something very important, and such that H1 of this X, it looks like, well, some number, something like this. I want it to look like this, okay? Because remember, I want to realize A as a direct summand in the homology of my finite color. So that's what I'm going to do. Okay. Okay. So let me first give you an idea of how to just construct a two complex that has homology looking like what you want. Okay, so I'm going to draw some pictures. So let's say I start with a surface of genus G. Okay, here's a picture. Okay, so here's a surface of genus 4. I can find in the surface some embedded simple class curve that is non-separating. So here's an example of one. Okay, that's a curve in my surface that's non-separating. I can cut along it. Let's say I cut. So once I cut along it, now I have two ends of it. There's this one, and there's this one. Okay. And now what I'm going to do is I'm going to take the quotient. So quotient each of these boundary curves by 2 pi over n rotation. Okay, so I can do this for each of these. So the resulting thing is a two complex, so it's no longer a two manifold, but it's a complex. So I get this two complex xn, a two complex. Okay, and here's an exercise. You can do this with, you can definitely do this with first year algebraic topology class. And the exercise is that if I look at the homology of this two complex, then what I get is 2G minus 1 copies of Z and 3 copies. Okay, so I can do something like this to get any cyclic, finite cyclic group that I want. And you can imagine that you can, if you have a large enough genus, you can do this sort of trick at different disjoint embedded curves to get the finite abelian group that you want. Okay. So that's the idea. Okay, so now let's go back to the setting that we have. Well, we have n, and we have a piece. Let's say in here, there is a hyperbolic piece. Okay. Okay. I'm going to do this just for the cyclic case, but you can do this by induction. So if I fix n, so this is an integer greater than 1, and I fix a large value r, very large, and a small epsilon. Okay, so what I'm going to do first, let me tell you that I can do this. I can find this is what's called a good curve alpha in MH. Let me draw a picture. So again, H can have multiple plus. There's a picture with 2 of them. I want to find a curve alpha that is good. I'll tell you in a second what good means, but some sort of curve like that. So okay, so what I mean, like, oh, actually, let me call this alpha naught. Okay. Make sure that I don't know what to say. Here, so alpha naught, so this is a curve in a geometric manifold, so I can say things about its length, for example. So alpha naught has complex length epsilon goes to, I think I want 2r over n, that's what I want. So, yeah. 2 alpha. Actually, I don't want epsilon, I want epsilon over n close to this number, okay? Why? Because I'm going to now let alpha be the n power of it, so it's going to be epsilon close to what I want. And height less than log of r over n. So I want, oh no, just less than log of r. I haven't told you what height is, but this is some measure of how far we are from the crust. So the point is I do want to ensure that there's some distance away from the crust. And this is very important because when I glue this piece back into my full 3-manifold M, things go wrong and some things are happening on the crust, okay? Because this is where I glue into the other JSJ pieces. Okay. So I'm going to find this curve. And I'm going to use, I'll say this here, and I'm going to use the machinery on right. So this is a big machinery that I was talking about. So their preprint came out in 2018, but it was published in 2021. So it's fairly recent, and again, it didn't exist at this time that Sven wrote his paper. But I'm going to use their machinery with some modifications. To construct a surface S with an immersion into my manifold NH, where, and with a simple closed curve that's non-separating C in my surface that maps to alpha. Okay, so you can sort of see why I'm doing this. I'm particularly choosing this alpha to be n times this alpha naught. And I'm going to play the same trick that I played here, where I'm going to cut and I'm going to do this quotient. And I have to be very careful to ensure that everything that I want works out right. But this is really the idea here. And I'll say, I'll write it over here. So I can now carefully ensure that I can cut and quotient to get this immersion of xn into my MH. To my MH. Notice that you have to be really careful because when you cut here, you get these two curves that are, well, they're homotopic in the manifold. So in particular, when you look at them in the fundamental group, they come from conjugate elements, but they're not equal. Okay. or we want to make sure that they're not equal so that we can cut and still get this embedding or this pi1 injection here. Okay, so to get this, which is pi1 injective and relatively quasi-convex. Oh, I'll mention something here. I haven't talked about what relatively means. Oh, I guess I also haven't talked about what quasi-convex means. But the relative really has to do with relative to this tori boundary. Okay. Okay. Anyway, so that's important. So now that I have this, because I have this subgroup as being relatively quasi-convex, that means that I can use these virtually special theorems to find a virtual retraction. So then use virtually special theorems to find a retraction like this. And all of this is to give me now that when I look at the H1 of this cover, well, this is going to look like the H1 of X, oh, this is Xn, plus some stuff. This is plus like the kernel of star. Okay. So this is what I get. And in particular, since I chose this to sort of contain Simonetsky, now I can realize this cyclic group as this H1 of this finite cover. And again, like I said, if you have large enough genus, you can cut along different things to get whatever finite beta you want.
Excuse me, the retraction was happening at the level of fundamental groups, right?
Yes, that's right.
Pi1.
Yeah.
Thank you.
Okay. Okay. So that's sort of the idea of how the proof works. And again, there's a lot of things that one has to be careful about. You have to be careful about how everything glues up into the full manifold. And getting these pi1 injections are one has to be really careful too. But I want to just end with a corollary of this result. So the way it's stated, it just applies to these large class of 3 manifolds, of these compacted reducible 3 manifolds. But could you say something in higher dimensions? Well, perhaps. Unfortunately, we don't really understand higher dimensions that well. Even once you go to dimension 4, things can get wild. However, we can say the following. Oh, and also, and like things can get wild, like you can realize any finitely presented group as the fundamental group of any 4 manifold. For example, you can realize any finitely presented group as a fundamental group of a 4 manifold, for example. So once you go dimension 4 and above, things can get really crazy. But here is something that we can say. So if n is an arithmetic hyperbolic. Oh, I need to add a word here. This is standard. So if n is a standard arithmetic hyperbolic n manifold of finite value, then also virtually has any prescribed torsion in homology. So I'll say that these are very special types of n manifolds. They're also spherical, but they're nice and I like them. So we can say the same thing in those cases too. Okay. And maybe I'll end here and I'll have questions.
Just thank Michelle for a very interesting talk. Are there any questions?
Do you have an example of like this arithmetic? Like, does it, like when I see the word arithmetic, I'm like, is there any kind of like actual number of things that goes along with it? Like, do you have like an example of like?
Yeah, I'll give you the easiest ones that you can construct. I'll tell you first that the isometry group for hyperbolic n space, this is this group. Let's say it's plus n1 with real coefficients. Okay, so these are the, let me just remind you, these are the n+1 times n+1 matrices with real coefficients that preserve the form of signature in 1, so n positive eigenvalues and 1 negative. Okay, so this is the isometry group of Hn. And if you take this group, let me just call this, no, let me just leave that. If I take now gamma to be, say, I take this group, and I like intersect it with matrices GL1 plus 1 with integer coefficients, for example. This group is a discrete subgroup in here, and it has finite covolume. So again, if I take Hn, and I quotient by this, I get a finite volume hyperbolic orbifold. So this is unfortunately not a manifold because there are some torsion elements in this group, but you can easily find finite covers that are torsion free. So you can easily find finite covers of this orbifold that are manifolds. Okay, and this is like the standard example of a arithmetic hyperbolic n manifold. That's fairly easy to construct, and you can see that in the case where n is 2, when you do this, you get the modular group. So if you've heard about the modular group or like the modular surface, but I guess it's not a surface because this group has torsion, but it looks like this. Okay. This is a picture of what it looks like. You have this cusp here. There's a cone point of order 2 and a cone point of order 3. That's what it looks like. And that's in the case of n is 2, and you can find finite covers that are manifolds.
Other questions? Those coming from our virtual attendees. If somebody wants to speak from the Zoom connection, just unmute yourself and speak up. In the meantime,
yeah, I've just unmuted myself. Hi everyone. Hi Michelle. And this is Peter here. So I'm still at the level of understanding the things that you say. I'm afraid. So if you have virtually any prescribed torsion in homology, does that mean, for instance, that what does that mean? Does it mean that if you take a homology group, like I think you're taking the first homology group, it cannot mean that that homology group has torsion of any prescribed order that you can imagine, I think. So it doesn't mean that, I think. And I think you're defining virtually in terms of finite covers. But for me, if I talk about virtually, it means that there is a subgroup of finite index with some property like this.
Yeah, this, but it is the same. I guess it's the same thing, because if you have a finite cover here, this is the same thing as at the level of fundamental groups. This also like this. This is a finite cover, and at this level, it's the same as just a finite subgroup.
Right. So my issue is that if say pi 1, so you've got a finite index subgroup, but if pi 1 of m tilde has some torsion in it, like that means an element of finite order has a certain finite order, right? Then pi 1 of m also would have that element of finite order. But I'm not understanding something correctly.
It's not torsion in the group, it's torsion in the homology.
Yeah. Right. So, yes. So if you take the homology, and are you always taking, like, I'm not clear if you're taking arbitrary homology or are you taking first homology only?
Homology with integral coefficients.
With integral coefficients, yes. So this would mean the abelianization has that. So for instance, a free group, if pi 1 of m happens to be free, then this could not happen because every subgroup would be free and the abelianization would be torsion free.
Actually, I forgot to say that this has to be at least 3. Because in the case when n is 2, then you get free groups.
Yeah. Anyway, so it's kind of is it a sort of opposite kind of statement? I mean, it's completely different to having a free subgroup, for instance. It's because to get torsion in the abelianization is, to me, is a strange sort of thing. Saying there's a lot of torsion about that.
Yeah, it is a strange sort of thing, which is why I think there's a lot more understanding in understanding the first Betty number, because that's just related to having free groups.
Yeah.
Completely different things, so we just don't understand that as well.
Thank you. This has helped me understand.
Any other questions? I have a short one. How does it contribute to the evidence to the conjecture?
It doesn't.
It doesn't.
Because there's no there's no control on the index.
I see.
Yeah, actually, special theorems, they don't really say anything about how to control the index.
Mm-hmm. I see. And you were talking about 3 manifolds, right, all the time, but suddenly in the end you said the corollary is true for n manifolds.
Yeah.
Okay.
Yeah, I'm happy to talk more about that maybe some other time.
Okay. Great. Yeah. Let's thank Michelle for the very interesting talk. There will be like topology peers, traditional topology peers at 4:45 gathering on first floor. Everybody is welcome. And at that I will end the recording.